For over a century, the electric grid operated as a strictly one-way physical pipeline. Massive centralized facilities like coal plants produced raw power, pushing it outward across thousands of miles of transmission lines to passive endpoints. The entire engineering premise of this legacy model relied on controlling the supply side. Because consumer demand was considered completely inelastic, people flip a switch and expect immediate power, grid operators had to constantly ramp generation up or down to match those consumption spikes. The introduction of large-scale renewable energy breaks that equation. Solar panels and wind turbines are weather-dependent, meaning the supply of electricity is now highly variable. If a heavy bank of clouds suddenly covers a utility-scale solar array during peak air conditioning usage, the grid experiences a severe supply deficit. When generation drops below the required load, the physical frequency of the alternating current plummets below 60 Hz. If that frequency decay isn't arrested quickly, physical hardware on the grid will automatically disconnect to protect itself from thermal damage. This cascading failure leads directly to widescale blackouts, leaving critical infrastructure offline and utility lines dead. Building thicker transmission cables or constructing more natural gas plants doesn't solve this. The vulnerability is a matter of information processing and precise timing. Raw physical infrastructure alone cannot fix it. To survive the integration of highly variable generation, the power network has to evolve into a cyber-physical architecture. The physical wires remain, but they must be overlaid with a high-speed digital nervous system. This requires moving away from the centralized control of a few dozen power plants toward the decentralized coordination of millions of endpoints. Instead of treating consumption as an immovable constant, electricity demand itself becomes an elastic, dispatchable resource. To execute this, everyday buildings and homes must be transformed from energy sinks into dynamic assets that communicate and adjust usage on command. This architecture requires three distinct tiers: an observability layer to monitor, a control layer to adjust, and an aggregation layer to scale. These transform local adjustments into a meaningful utility resource. By dynamically reducing demand exactly when supply dips, the grid mathematically rebalances itself. This maintains precise system frequency without requiring the construction of new centralized generation facilities. In any control system, operators cannot manipulate an asset without first observing its state. Early grid digitization attempts used automatic meter reading, which provided a basic one-way pulse of consumption data once a month. This was sufficient for billing, but useless for active grid management. The true foundation for a cyber-physical grid is advanced metering infrastructure, or AMI. These smart meters provide a permanent two-way digital communication backbone between the utility and the consumer. AMI captures a dense stream of telemetry. Instead of monthly totals, operators now receive precise metrics broken down into 15-minute intervals. Within those intervals, the meters report critical electrical parameters beyond just total usage. They track localized voltage quality, the real power being consumed, and the reactive power needed to maintain the electromagnetic fields in local appliances. This granular data routes through dedicated Wi-SUN or cellular networks, feeding directly back into the utility's distributed energy resource management system. Ingesting concurrent telemetry from millions of meters generates vast amounts of data, requiring utility software to process years of high-resolution records to identify usage patterns and isolate localized faults. The deployment of AMI proves the grid edge is no longer a blind termination point. It acts as a continuous telemetry node, actively reporting the health of the local distribution circuit. High-fidelity observability is a prerequisite, but it holds limited value unless it triggers a proportional control mechanism to stabilize the system. For decades, demand response meant utilities picking up a phone to ask large industrial facilities to manually power down factory lines during a crisis. Today, that manual process is replaced by automated demand response, or ADR. ADR relies on direct machine-to-machine communication.
When grid stress rises, the utility software dispatches signals over the internet to automatically throttle smart thermostats, HVAC units, and building control systems. This relies on standardized hardware interfaces, like the CTA 2045 port installed in modern water heaters, allowing disparate appliances to interpret and execute these network signals without software conflicts. This chart illustrates grid operations' temporal constraints. The central green triangle shows demand response acting between 1 minute and 1 hour. Here, ADR rapidly shaves peak loads. Without reduction, the system slips into service restoration, meaning rolling blackouts have already occurred. The automation executes micro-adjustments specifically designed to preserve end-user comfort. It might delay an electric vehicle's charging cycle by 30 minutes, or rely on the thermal mass of a preheated water tank, so the heating element can safely stay off during peak hours. These adjustments happen silently in the background, entirely bypassing the need for homeowners to manually check apps or alter their daily routines. By successfully implementing ADR, grid operators ensure consumer demand is no longer an inelastic constraint, but a highly programmable variable in the operational equation. Even with ADR, a scaling problem remains. A single smart thermostat saving 2 kilowatts of power is virtually invisible to a bulk grid operator managing gigawatts of demand across thousands of square miles. The solution is the virtual power plant, a software aggregation layer that bridges the gap between residential microloads and wholesale grid requirements. A VPP uses cloud architecture to link thousands of disparate edge devices into one controllable portfolio. The operational consequence is significant. Operators can now dispatch this aggregated software block with the same reliability, precision, and volume as a physical gas turbine. Regulatory changes, specifically FERC Order 2222, enable economic integration for these assets. VPPs can now bid this aggregated flexibility directly into wholesale capacity and energy markets. On a system-wide level, deploying a VPP allows utilities to avoid spinning up fossil fuel peaker plants. These physical plants are expensive to run and emit large amounts of pollution, operating for just a few hundred hours a year during extreme weather. By managing congestion directly at the edge of the network, VPPs also prevent the utility from having to tear up streets to install thicker distribution wires and larger transformers to handle load growth. By orchestrating decentralized demand at scale, virtual power plants mathematically and financially replace centralized physical generation. These concepts are not theoretical. Wholesale market operators are actively relying on cyber-physical structures to prevent system collapse today. This graphic from the Electric Reliability Council of Texas details tools used by independent system operators. Notice the engineering distinction between load resource participation, adjusting to real-time market signals, and emergency response service, which requires assets to drop load in exactly 10 or 30 minutes. To prevent the grid from failing before that 10-minute emergency response can activate, operators rely on the fastest tier of control, sub-minute frequency containment provided by inverter-based battery storage within the VPP. In a fraction of a second, these distributed batteries inject localized power to arrest frequency decay. This buys the grid operator the minutes needed for slower thermal and ADR resources to fully deploy. Actual grid resilience relies heavily on this orchestration. Operators stagger precise digital responses across millisecond, minute, and hourly timescales. The full cyber-physical architecture operates as a continuous loop. Edge telemetry feeds into a centralized control layer, which enables market-scale aggregation. Maintaining grid stability has shifted from a one-way physical supply problem to a bidirectional, high-speed optimization problem. To securely integrate renewable energy, the future grid relies on treating every appliance, battery, and vehicle as an active node in a decentralized balancing equation. If you want to dive deeper into the engineering and systems analysis driving our modern infrastructure, make sure to subscribe. We'll see you in the next video.